right, so this video on wave interference and standing waves is slightly different than some of the others because I am actually providing you with the video notes. You can print those out and follow along. And that's so that you don't have to get hung up on the quality of the drawings or the amount of writing that is involved. So in this case, we're going to first start by talking about wave interference. So we have discussed what we know about a single wave, that y is a function of x and t. That is a single sinusoidal traveling wave. And we've pretty much examined that in a lot of depth. And now what we want to do is look at the more interesting and more realistic situation of what happens when there's more than one wave in one location. Maybe that's because there's two speakers and they're overlapping in space and time. Or more likely, maybe it's because you're playing a violin and it doesn't create just a single standing wave. It creates multiple, not just a single sinusoidal wave. It creates multiple different frequencies of sinusoidal waves, and they're all overlapping in space and time. So if you have two waves overlapping, the good news is that they do exactly what you'd expect. It's called a superposition principle, and if you have multiple waves, they just add up. It's an algebraic sum of the individual waves, and that phenomena is what we call interference. So we have here this idea of interference, and what we're going to do is look at two kind of extremes of interference. When do things interfere in a way that makes it as large as possible, and when do things interfere in a way that makes something as small as possible? So the first one, when things get as large as possible, we're going to call that constructive interference. And this is where physics got it right? If you constructively interfere, you're interfering in a way that adds to itself. And so that's going to be the largest amplitude possible. And that's going to happen if we have this wave here, and that wave is superimposed with another wave. So I've drawn them separately on this handout, but you can imagine that they're actually overlapping in space and time. So that's the first wave. And then if I add it to a second wave, and their crests line up and their troughs line up, right? Then I'm going to get the largest possible wave, because if I add these together, my peaks are going to add and I'm going to get double the amplitude. And so this is going to happen when, in terms of when you get constructive interference, it'll happen when our phase, the distance that one wave is shifted relative to the other one, when the phase is going to be off by a factor, an even factor of pi. So for example, down here, we would have a wave, a starting wave, and then a wave that, if superimposed, would constructively interfere because of the addition of a 4 pi to its phase. So that makes sense, right? That we're going to have two sine waves and they're going to get the largest amplitude possible if they match up, if they're in phase, as we call it. So then the other extreme is going to be destructive interference. So destructive interference is going to be when the opposite happens, when we would have one wave where its peak lines up with the trough of another. So a peak lines up with a trough, and you can actually end up, if they're the same amplitude, with 0 amplitude. So you can have two waves overlap in space and actually have no resulting amplitude. So the crests line up with the troughs, and that's going to happen when the phase is off by an odd multiple of pi, right? So half of a cycle. So pi or 3 pi, so, a full cycle plus a half. That has to be shifted by essentially half of a wavelength, which would be half of a cycle. So an example of that would be, let's say you have our starting wave, and then over here, then the phase shifts by some odd multiple of pi. That's the fundamentals of interference. You explore that a lot more in the second semester of physics when you also look at optics and you do some interference with optics. In this class, we're going to focus on one key application of this wave interference, which is called standing waves. So standing waves, again, it's our key application in UP1 for the wave interference, this idea of constructive and destructive interference. And it's a really, really cool phenomenon that's going to happen when you're going to have two traveling waves, they're traveling in opposite directions, and they're in phase with each other. So what's going to happen then is they're going to constructively interfere. And then we're going to get something that looks like a standing wave. So there is a supplemental video that then lets you visualize that and allows you to see that interference as it happens and not just the math of it. So the main idea for standing waves is that it's two traveling waves. They're heading in the opposite direction. They're in phase with each other. So they have the same wavelength and the frequency. And the only difference then between the two is the direction of motion. So that's going to be the kx plus omega t, that'd be traveling to the right. Kx minus omega t would be traveling, kx plus omega t is traveling to the left. Kx minus omega t is traveling to the right. And so you would have identical waves overlapping. They're in phase with each other. And so then you get this traveling, this fundamental idea of two traveling waves that will overlap and create a standing wave. So the supplemental video kind of shows this to you. What it is basically, it's if you just imagine a jump rope and you kind of make the jump rope, instead of spinning it, you kind of just make it go up and down and up and down and up and down like this. You would also have, higher modes of oscillation that you're going to get as well. So that supplemental video will really help with that visualization. So the key idea here is that you have two traveling waves overlapping. What we do here then after this is just going to be some sort of fancy math that involves our using of one of those trig identities of what happens if you have a sine of a minus b plus the sine of a plus b, and you can actually use it and you can simplify that result. Now, whether or not you write it out in its long form or in the simplified version, is not important. What matters is that you know that the standing waves get formed when there's two traveling waves traveling in opposite directions. Now, if we do look at this simplified result for what we end up with, it is useful, and that's going to be because it's going to allow you to see the differences that happen as a function of where you are along, say, a string. So basically what this means is if we look at this first term, this is our standing wave vertical position. The amplitude is basically going to depend on the position. Sine of kx depends on where you are along the string. So some parts of your string, if we have a string over here and here, if you have, and we just imagine kind of one of these standing waves like this, it's going to oscillate kind of up and down and up and down, and that's again caused by two traveling waves. Then where you are along the string dictates the total amplitude of the simple harmonic motion for that portion of the wave. So the amplitude of the simple harmonic motion depends on position along x, where you are on the wave. And then the sine omega t term basically just means that it's each particle is executing simple harmonic motion, as I've described with the green, with the red arrows, and then now highlighted in green is that we see that they're each undergoing simple harmonic motion, but that with a variable amplitude depending on where you are on the string. So that's what allows us to trace out this really cool thing. It's called a standing wave because even though it's two traveling waves overlapping, it looks like it's standing still. So that's where the name comes from. So how do we get, and why are we talking about this, what seems like an obscure case of having two traveling waves overlap in space and time that are in phase? And it turns out that that happens all the time. You can create standing waves by reflection off of the end of a string. So a guitar string fixed off both ends, you pluck it, you send a traveling wave, it reflects. The only things that don't kind of disappear instantly are going to be the ones that constructively interfere. They're going to be the standing waves. The same thing happens off reflection off the end of an organ pipe, etc. So to create a standing wave, we have a couple definitions that we're going to learn. If the end is fixed, then we need to have a node at the end. What we mean by that is if I have this as my fixed wave, it would have this short sort of shape to it. This would be the fundamental mode. We'll get to those definitions later as we scroll. If the end is open, like an organ pipe, then you're going to have an antinode at the end. So if it was something open like this, you might have an antinode, and your shape of your standing wave might be different because it's an open end. And so that would be, if it was an open end, you would have an antinode at the end. So those are the conditions for what would create this constructive interference. Because if you don't have a node, you get a reflected wave, but it's not in phase. So in order to get a reflected wave that's in phase, you need to meet these boundary conditions. All right, so that's going to now bring us to the last part of this video. And for this one, I am actually going to basically just encourage you to highlight the entire thing. And that's going to be because this is really the heart of the problem solving that you're going to do involving standing waves for a fixed string, for a string that's fixed at both ends. And so this, along with the supplemental video, will allow you to kind of visualize these pretty nicely. So in this case here, we are going to have the standing wave fixed at both ends. And then in this case, a couple key things to point out. First, we're going to define something as mode number. Mode number is the number of the mode that we're talking about, because you can create different shapes. You can have kind of this very low mode, this fundamental. You can have higher ones with more nodes and more antinodes. The mode number is n. When we say mode number 1, we mean the fundamental mode. We sometimes also will call these harmonics. And so the second mode then could be the second harmonic, etc. We've already talked briefly about what a node is. A node is a place of 0 amplitude. An antinode is a place of the maximum amplitude. And a lot of times standing waves are drawn with a solid line and the dashed line to show that this is actually an oscillating up and down situation. All right, so then what we can do is, what you can do is actually just look at the picture and try to decide what the wavelength would be of a particular mode in terms of the length. So if we know the length of the string here, L, then this would have a node at each end, but if I were to continue what that would look like, it would extend over, right? So that one full wavelength would actually be equal to 2L. So that's where I would get this result, that lambda equals 2L for the fundamental mode. And I did that by looking at my picture. Let's look at a higher mode. So now if I look at a higher mode, this would be mode 2. I still have that same length. Now I can see that I actually have one full wavelength. I have a node, and a node. I have 2 antinodes. And so I have this one full wavelength within my length L, which means that then lambda equals L for this one. And again, that's from just looking at the picture. If we keep on going, this would be the next one. I can add on an antinode each time. This would be mode 3. I would then have one node, 2, and then all the way over. So I have my 3 antinodes. You can see that the wavelength here is simply going to now be 2/3 times the length. And again, that came from looking at the picture. So the wavelength in terms of L comes from looking at the picture. And then this keeps on going. You can have n equals 4, 5, 6, 7, etc. So for the steps for problem solving then, the first thing, and these might change order depending on what the problem asks for, but these are the steps that you use in any particular order. One thing that you can always do or try to do is try to get lambda in terms of L from the picture of whatever mode you're talking about. Then remember that we can get the speed from a wave on a string. So the speed for a wave on a string is tension divided by the square root of tension divided by linear mass density. And then the other third key part of this is that we're going to use V equals lambda F. And that'll allow us to get the frequency of a particular mode by combining in all of these things. Okay, let me know if you have any questions.